Hi all, welcome to this video. In this video, today we are going to explore one of the most advanced artificial intelligence system for object detection, which is Qwen3-VL model. These are the table of contents that we are going to discuss in this particular video. But before getting into the actual Qwen3-VL model, first let us understand what is vision language model. As we all know, traditionally we had two separate AI branches. One was computer vision. This particular branch used to detect what is present in an image. Then the other branch was natural language processing, which understands and generates text. Now, this vision language model combines both. It can detect an image and at the same time it can understand and generate text. Basically, when we are presenting some picture, it checks what objects are present, what and how are they positioned, what is happening between them, why something is happening. So instead of just recognizing a dog, it can say a brown dog is sitting near a tree. So this is not just detection, it's the understanding which is possible because of this vision language model. This was just the introduction about VLM. Let us try to understand what is the evolution of vision language model, and to make this concept easier throughout, we will use one common example, that is a table that contains a cup, a book and a pen. Now we will see how different generations of VLM will interpret this particular scenario. Earlier there was stage 1, which was early scene based detection model, which was introduced in year 2012 and lasted till year 2015. The examples were AlexNet, VGGNet and ResNet. Basically, they use technology called convolutional neural network, which is nothing but CNN. So these were the first breakthrough models in computer vision, and their job was simple. They used to look at the image and classify the most prominent object. For example, if we give them our example, they do not understand multiple objects. They will only extract visual features and it will give one label. They will give output simply as cup. So they basically ignore the book and a pen because these models were optimized for single level classification, and they cannot just generate language, answer questions or understand any relationship. So this was very basic sort of the model which was introduced in the earlier years. Then stage 2 came. In the stage 2, there was introduction of attention mechanism and transformers. In the year 2017, it started and lasted till 2020. The examples were vision transformers, then DETR, and the technology shift was CNN to transformer based visual understanding. So now in this stage, with the introduction of the attention mechanism, this model could actually focus on different parts of the image instead of processing it uniformly. So when we provide the same example, cup, book and a pen on a table, transformer now can process multiple objects and it can be able to notice multiple details. For example, with first model we just got output as cup, but with this model we will get output as objects detected, cup, book and pen. So this was like a major improvement because the model does not ignore the secondary objects like the first model used to do. But they also had some of the drawbacks, you would say. For example, they still could not identify relationship like pen beside the book or cup in front of the book, etc. So this was the drawback of this model. Then after this, stage 3 was introduced, which was of multimodal vision language. It was from year 2021 to 2023. The examples were Clip, Blip and Flamingo. And here the introduced was image plus text fusion. So this generation integrates visual understanding with language, and these models now receive image and text in shared space, so they can just describe, caption and answer basic questions. So with our same example, output becomes more meaningful, like a cup, a book and a pen are placed on a table. This was the output from this model. So this means the model now recognizes all of the objects. It can also produce sentences and it can also answer basic questions like, is there a pen on the table? It could just say yes. But this model also had particular limitations. Like no bounding box coordinates were there, no spatial relationships beyond simple descriptions were allowed. Then it had very limited reasoning, no multilingual OCR support. So these were the drawbacks of this particular model. And lastly, there was this stage 4, which was advanced VLM, which started from year 2024 and 2025. Obviously, the most popular example of this advanced VLM is GPT-4V and Qwen3-VL, which we are going to see in this video. So what happened? This stage represented the highest point in the evolution so far, because these models can detect every object. It also provided exact positions, understand object relationships, and it also performed logical reasoning. So the same example that we are taking, a cup, book and pen. So with this model, the output would be the detected object is cup at the coordinate xyz, book coordinates xyz, pen at the coordinate xyz, and entire relationship also captured. For example, the pen is placed beside the book, the cup is in the front of the book, and it also used to draw reasoning like pen is a writing instrument, a book contains information, etc. So this is the first time the system not only sees and describes, but it also understands where objects are located. It also connected visual data to semantic meaning, and it also answered complex queries like which object can be used for writing. The answer is pen. This was the capability of this current model that we are going to talk in this video. So this was the overall evolution from year 2012 to current 2025 year. Let us discuss now the capabilities of Qwen3-VL model. The first capability is rich visual understanding. It is very good at recognizing object. Whether the object is big, tiny or even half hidden, it can still identify it. For example, even if only the dog's tail is visible, the model can still figure out it's a dog. It also understands the overall scene, whether it's indoors or we can say it's outdoors, what's the weather looks like. So it doesn't just see the things, but it also understands the context of it. The next capability is deep image text reasoning. It can connect language to the exact part of an image. So if you ask where is the red car, it knows which region of the picture you mean. It even understands diagrams, charts as well as table. So if you just give it a bar graph, it can tell you which bar is the highest or compare values like that. Then the third capability is long context multimodal processing. So this Qwen3-VL can handle a long or huge documents, not just one image. If you give it a 50-page PDF, it still remembers what was on the page 1 while reading on page 50. And not just the PDF, it also understands videos. It follows object across frames and understands events over time. Like someone is picking up a ball and then throwing it like that. Then the last capability is advanced OCR and document parsing. Finally, it is very strong at reading text in images, printed text, handwriting, multiple languages. Even if the image is little blurry, it also understands the structure of document, such as this is the heading or this is the paragraph or this is a form field like that. So it doesn't just read text, but it understands how the document is organized. So overall, if we have to discuss these capabilities, Qwen3 is a very powerful model because it not just able to see, but it can read reason as well as connect the every picture together, and it gives the better analysis of the same. Now let's talk about our Qwen3-VL. How exactly this model processes text, images as well as videos using a single unified pipeline. On the screen you are able to see a diagram. This diagram might look complicated at first, but once we talk through it step by step, you will see how everything is getting connected. Let's start from the very top. In this system you will be able to see we can give different kind of inputs. Normal text, very large images, very small images, medium resolution picture or even videos also. So you can see these as different colored squares at the top of the diagram. The gray squares represent text token, while the various colored squares represent visual tokens coming from images or videos. You will also notice this small timestamp marker which are used for video frames. Now look at these three pictures shown in the diagram here. Picture 1 is an extremely tall image, almost like a long block screenshot with a height of around 9376 pixel. Then we have the small picture 2, which is very small, around 32 by 256 pixel. Then we have the third input, which is picture 3. It is a medium sized, around 800 by 1440 pixel. And on the right side you have video 1, which consists of multiple frames, each around 448 by 736 pixel. The point here is to show that Qwen3-VL doesn't force every image into the same size. Instead, how we are seeing it, it takes each input in its native exact resolution pixel that has been defined. So this is very important because it preserves all the details in large images while also being efficient with small ones. Now, all these images and video frames first enter the vision encoder here, which is like we can say heart of the visual understanding system. Job of the vision encoder is to take raw pixels and convert them into something the language model can understand, specifically vision tokens. Now, these tokens are basically mathematical representation of what the model sees. The number of tokens depends on the resolution of the input. For example, picture 1 we saw, it is very huge in size. So it has produced 11,427 tokens. Whereas on the other hand, we saw picture 2 is a very tiny and it only produced only 8 tokens. Third picture created close to 1125 tokens, as you can see here, and video generates their own token sequence along with timestamp, which helps the model understand motion as well as changes across the frame. Now, once the vision encoder transformer, like everything has been transformed into the tokens, something interesting will happen here. This vision tokens are mixed together with the text tokens and then they are sent into the main language model, which is Qwen3 dense/MOE decoder that you are able to see at the top. Now this decoder contains multiple layers shown on the right as LLM block 1, block 2, block 3 and so on. So this is where the real reasoning happens. Inside these blocks, the model combines what you asked in text with what it has seen in the images and videos. It will also understand the relationships, context object, actions, timings, everything. For example, in the video shown, you can see there is one robotic hand which is interacting with an apple, because the model receives not just the frames but also the timestamp. It can understand what is happening over the time, like whether the hands are moving, whether the apple is lifted, or how the scene changes between the first second and the 8th second. This gives the model the ability to interact action, not just the static scene. So this is exactly how processing happens for the video input, that the fourth input that we are attaching. Now, if you ask the model something like what is happening in the video, or describe the blog image, or compare picture 2 with picture 3, this model uses both visual tokens and the text token inside the decoder, and then by processing that it will form a meaningful answer. So there is no system or no separate manual alignment is needed. Just one continuous flow from images and videos into the vision encoder and then into the language model and finally into the output you receive. So in simple terms, if I have to summarize, this entire diagram is showing us how Qwen3-VL accepts multiple modalities, then how it converts visual data into tokens as we have seen, then how it mixes it with the text understanding, reasons through it, through let's say multiple layers that we are seeing over here, and then how it is producing the responses. So this ability is seamlessly combined vision language, and this is exactly how this Qwen3 model is working. Now the way we have learned Qwen3-VLM model processing, we also need to understand how vision language model actually takes place the entire processing, right? So for that purpose, we will simply take a universal example, a dog playing with a ball in a park. So the first stage, initial stage includes is image encoding. That basically means breaking the image into multiple pieces. Imagine we show the model the picture. Let's suppose that picture has a dog, a ball and green grass as we have discussed. So this model will basically cut images into many pieces. We call it as patches. It's like tiny square tiles 16 into 16 pixel each. Now each tile which has been broken becomes a vector of number representing what's exactly inside the patch. Now this patch can be anything. It can be color, it can be shape or pattern. Now because this image is in pieces, we also add positional encoding. When we add positional encoding, our model exactly knows which patch came from top, which came from bottom and which patch contains dog's face, grass or the ball. Now at this stage the model doesn't see a dog, but it sees hundreds of tiny representing parts of the dog, ball, grass, etc. The second stage over here is visual feature extraction, which means understanding the image. Now the model tries to understand what these patches mean. The vision transformer that we have seen, it looks all these patches and then it asks questions like this brown patch, is it a fur? This round patch, it can be a ball. This green patch, this can be a grass, like this. So using this self-attention, the model learns how patches can relate to each other. So this step basically helps the model understand the overall scene. There is a dog holding a ball standing in a park. So by this stage, these things will be clear. Then the third stage comes into the picture, which is cross model alignment, which is like connecting the picture to words. Now the model has visual understanding, but it still doesn't have anything words as present. So the next thing it does, it aligns the image concept with language concept. For example, the visual pattern of fur, it maps to the word dog. Then a round colorful object, it maps to the word ball. Green texture background, it will map it to the grass park. So this creates a shared space where both image features as well as words can live together. Now after this stage, stage 4 comes, which is language generation, creating the final description. Now finally, the language decoder starts speaking. It looks at the visual features, dog, ball, park, etc. Then the language rules. It checks the grammar, sentences, flow, etc. and the previously generated words. Then it generates text one word at a time. Example process, it sees a dog, predicts a dog. It sees the ball, playing with a ball. Sees a park, in a park. Final output becomes a dog playing with a ball in a park. So if you have to summarize this, for example, we have given the image dog plus ball plus park. Step 1, it will break the image into small tiles. Step 2, it will understand what each tile represents. And in step 3, it will connect visual concept to language concept. And finally, it will generate the final sentence describing the entire picture. There are different versions of the Qwen3-VL model and each version has a different size or different speed and it is basically used for different purposes. We are going to discuss the 4 models. The first model is Qwen3-VL 2B. This is like the smallest model and 2B is the version. It needs very little memory. It also works fast and it is great for lightweight devices like mobiles, tablets or real-time application. Then the next one is the 7B model. This is the balanced middle option, not too heavy, not too light. It gives good accuracy without needing extremely powerful hardware. Then we have the 14B model. This one is longer, larger, slower but much more accurate. It's used when you need very reliable results, for example analyzing documents or detailed images, etc. And finally, the biggest model is the 72B version. It needs huge memory and is the slowest, but it gives the best possible quality. This is used mainly for research or you can say critical high precision work. Now let us quickly look at how Qwen3-VL performs compared to other well-known models like GPT-4V and Gemini Pro. So these benchmarks basically show how well a model understands images, text as well as charts and documents. The first parameter is COCO, which is object detection. In object detection, Qwen3-VL 2B performs well, but is slightly behind GPT-4V. Qwen scores around 48 MAP, while GPT-4V is about 52. So GPT-4V is strongest here, but Qwen is still close. Then the text VQA, answering questions from images. When it comes to reading text inside images and answering questions, Qwen scores about 78 or you can say 71%, while GPT-4V is at 78%. Again, Qwen is good, but GPT-4V leads in this parameter. Then DocVQA, document question answering. For document understanding, things like reading forms or PDF, Qwen performs very strongly. It scores 85%, which is close to GPT's 4V's 88%, slightly above Gemini, you can say. Then chart QA, understanding charts and graphs. In chart interpretation, Qwen scores around 76%, Gemini is slightly higher, and GPT-4V leads with 80%. So Qwen is competitive, but we can say not at the top, like a top performer. Then the multimodal object reasoning. This is the most complex test. Multidiscipline reasoning. Qwen scores about 45%, while GPT-4V goes up to 56%. So this shows the bigger models still handle very complicated reasoning better. Down the line, if we have to give the analysis, it would be like overall Qwen3-VL 2B performs well for its small size. It's not as strong as GPT-4V, but it stays close in most tasks, especially in the document understanding. The main takeaway is Qwen is efficient. It is also competitive, especially considering how lightweight Qwen3 model is. So that is the good thing about this model. Now let us move to the implementation. First thing that you will do is you will click on connect, then you will take this runtime Python 3 and T4 GPU, and then you will save this. Now wherever you will find this code lines, you need to run this. For example, first we will run this, then config this Colab environment, import OS, GPU configuration. Lastly, we'll do the install dependencies, load dataset, import OS, model loading, everything. So every block of code you need to execute in sequence. Some of the code will take more than 3-4 minutes, like loading the model, and few seconds for the helper function. Like that you will have to execute every module. And then here below you will be able to see we are pasting just image path as input. We are passing it, and then our output is getting generated. There are multiple applications that we have mentioned in this particular project. For example, this is PPE kit related to it, as you are able to see on the screen. This is the other application, healthcare PPE monitoring and equipment detection. Here we will provide image of healthcare, then it will get detected. Then the other application that we are able to see is this, detect man and woman. So we will provide the image of man and woman, it will get detected. Further, smart traffic management. This is one of the application of the project that we have developed. We'll upload image as it is. So all below in this Colab file you will find multiple application like this, furniture detection, etc. So do not get confused. Every aspect how we are supposed to run, we will see step by step. Now before running Qwen3-VL, we just need to make sure our system is up to date and ready. There are simple 3 things that we have to check: the hardware, software, as well as the Google Colab setup. Now at minimum hardware requirements, we need a GPU like NVIDIA T4 with GB of VRAM, 16 GB RAM, and about 20 GB of free storage, which is to be noted. But if we want smooth performance, it's better to use something stronger like an NVIDIA L4 or A100 with 32 GB or more RAM. And for production level usage, companies usually run multiple A100 GPUs with high bandwidth networking. Then software wise, it's very simple. We need Python 3.8 or above, CUDA 11.8 or higher for GPU acceleration, and a recent PyTorch version. Basically PyTorch 2.0 or above will be working. Then if we are using Google Colab, the process is very quick. First step is that we have to use a Hugging Face token. This token is simply which will give us permission to download the model. And if we want to obtain this token, Hugging Face token, you just have to go to your Hugging Face account setting. You have to click access token, create a new token with read permission, and copy it. That's the token we paste into the Colab. Let us see how to generate this access token. First we will redirect to Hugging Face. This is the website. Then here on profile, if you click, you will be able to see access token. So we will simply click on this access token. Then this option, create new token. Then we have to put some token name. It can be anything. I'm putting it as access token. And then if I scroll down, I'll see a option of create token. I'll click on this, and this is the access token that has been created. You should just copy it and paste it in the Colab. I'll tell you where to paste in the Colab. The access token that has been generated, we have to paste it here. You see the key symbol, you have to click on this on the Colab itself. Then os.environment, we have set environment name as HF token. Make sure you use the same name. In the name value, you have to paste HF underscore token. And then in the value, you have to paste your key that has been copied. Next, we have to mount Google Drive. So Colab can access our data set, whatever images or let's suppose files we want. The model to read should be inside the Drive folder. For that, you'll simply click on Run. Then you'll get option to select your Google Drive account. As you can see now, mounting is done. It has executed. Next up is uploading dataset on Drive. Now we have to upload the files or the dataset on our Drive itself. For that purpose, first you should download this zip file. You will get this zip file of the dataset. You will simply extract all the data. Then on the Drive, you will click on New, then Folder Upload. Then you will choose the folder, unzipped folder, and you have to upload it same way. Uploading might take some time. For my case, it is taking 1 minute. All the 38 images that are present in the dataset have been uploaded now, as you are able to see. Now mounting is done. We will simply run this import OS command. Then we have this green tick, that means execution is completed. Next we will run this GPU configuration. See, this has been executed. Then we also need to install some dependencies. I'll run this pip install Qwen3-transformers. It will add all the necessary dependencies. Now we have to load dataset. For that, we'll click here. Then we'll go to our Drive that has been connected. Then in my Drive, now we will try to locate to our folder where all the files are present. Now as you are able to see, my files are present in this data Qwen3-VL. I'll simply copy path. And now I will paste it in here in double quotes. Now I will run this. Now we are running this block of code. You are able to see these lines. Let us wait, it is getting executed. So each line you are able to see here is one of like the part of the model where the files are getting downloaded. The first few files are, you are able to see, these are just configuration files. For example, preprocessor config.json. This file will tell you how to prepare images. Then tokenizer files, these files will tell you how to how text should be split into tokens. Then this chat template.json, this will tell you how a chat conversation, if entire chat conversation, how it is formatted, this would be told by this. Then config.json, this is like a file which tells the model its own structure. Structure can be either layers, heads, etc. So these are basically instruction and settings. And finally the big file called model.safetensors. This is like a big file, it is downloaded, and this is like the actual model, the learned weights like the brain. That's why this is large, and it is about 4 GB as you are able to see here. So overall these small files are nothing but the rules and instruction, but this big file is the real model of, you can see. Then next we have also used some of the helper functions that we have created. QuenDetect, it is a helper function. Basically this will act as an interface between our code and the Qwen3-VL model that we have used. You can say the primary responsibility will be like to sending an image and then detection of the request to the model and receiving the output. So this is the purpose of this function. Let us see step by step. The function Qwen3-detect takes 3 inputs, as you are able to see. First one is an image object, the other is a target string representing the object to detect, and then lastly it takes an optional max new tokens parameter. So the purpose is to ask the Qwen3-VL model to identify a specific object inside the given image, and it will return bounding box coordinates in the valid JSON format. Now inside this function, the first operation is device selection. This line, device equal to CUDA if torch CUDA is available, else CPU. So basically this line will check whether a GPU is available. If yes, the model will run on CUDA, otherwise it will fall back onto the CPU. So this will ensure that function adapts automatically to the hardware whichever is the available during runtime. Then the next stage is the prompt construction. Prompt F detect the object target in the image. So this prompt gives like an explicit instruction to the model what object to locate, then what format of output should be provided, and basically this will be provided in the JSON format as we have already provided into the prompt. Now preparing the message block, the model expects input in a specific message based format. You are able to see the structure. The function construct message role user content type. So this structure basically will combine both image as well as the textual instruction. Then we will have to convert the input into model readable format. So before passing the message to the model, we must convert it into the tokenized as well as tensor based format for the Qwen expects. So for that purpose we are using this input equal to processor.apply, chat template, tokenize true, and generation prompt true. So this way we will organize the message in the model's conversation template, and then we will tokenize the text, and then finally we will convert everything into PyTorch tensor. Then we will have to running the model, which is nothing but the interface. So this model is executed inside this torch no grad. Basically this block we are only performing interference. We are only performing inference, not training. So this generate function processes the image and the prompt, and at the same time it produces the model's output token. Then we remove prompt tokens with this trimmed output statement, and then we finally decode the token output into the text. So this result text equal to processor batch decode trimmed output. This produces the final JSON text containing bounding box coordinates, and then endly here we are returning the result. So this is the first helper function and the purpose of this helper function. Now there is one more helper function which is used, that is annotate image. The previous function basically focused on detecting object and it helped in obtaining bounding box coordinate, but this function will be responsible for visualizing those detection on the image. So as we are able to see, first we are doing import supervision as SV from PIL import image. Basically supervision is a utility library commonly used for drawing annotation on the images, and this image from PIL will allow us to work with image objects. Next, the code defines a custom color palette, color equal to SV color. So this palette assigns a set of predefined colors to bounding boxes as well as the labels. In the output of the image you will be able to see boxes drawn with colors. So this is because of these lines of code. Then the function definition and parameters. The function annotate image will accept image, the original PIL image, as first parameter. Then detection is like parsed earlier bounding boxes, labels or classes. Then smart position, this is like an optional parameter that adjusts label placement, so it will avoid overlapping. Then resolution based scaling, to maintain our consistent readability across different images and sizes, we are computing scaling values. Text scale equal to SV calculate optimal text scale. So this helper function automatically will choose appropriate text size and bounding box thickness based on the image resolution. So this will avoid some situation. Then choosing a coloring strategy. If class IDs are present in the detection result, the function will assign colors based on the class identity. See, color by class, detection class ID is not none. Then initializing the box annotator. With the scale and coloring decided, the function prepares a box annotator. Box annotator equal to sv dot box annotator. So this object is like responsible for drawing the bounding box rectangle. So it uses a color palette, then color strategy, as well as appropriate line thickness. And then we are doing this initializing the label annotator. And the label annotator has three key parameters. One is the text scale, the text color, and the smart position. Then we are applying this annotation, annotate image, image dot copy. Then it applies the two annotator one after another. We are able to see these two lines: annotate image box annotator and label annotator. Then endly we are returning the final output. So if we have to summarize, this function is responsible for drawing the boxes around the images that has been provided as the input. Now let us run this code. We will upload the image from our dataset. I'll simply go to the folder of my dataset. Then I'll take the image path, worker safety image. I'll paste it here inside image path, and here you are able to see I have put target object as safety helmet, goggles, and safety jacket. So basically these three items will be targeted in the output that will be generated. So this might take some time, but before that let us view the actual image. In the actual image you are able to see there are three workers who are wearing yellow helmet, gloves, and safety jacket. So whatever is the target object we have given, as per that our model will detect and produce the output. Let us see the output. See, here you are able to see in the JSON format, bbox 2D, safety helmet, safety helmet, safety helmet. So these are the number of safety helmets it has detected. Then the goggles, and in the image you are able to see the goggles, jacket, etc. are highlighted. So this is the capability of this model. Now I have edited my Colab file and I have added gloves in the target object. Previously it has only detected safety helmet, goggle, and safety jacket. Now our model should also detect gloves. Let us see the output generated. See, now in the image you are able to see gloves. 6 gloves are detected. So this is how you can edit in the targeted objects to achieve the desired result. Now let us see one more application, healthcare PPE monitoring and equipment detection. I am taking new image. I have copied the path of this image. I have just pasted it, and now the target object is wheelchair. Let me just run this. As you are able to see the wheelchair has been detected. Let's suppose I want to know about the oxygen cylinder also. So I'll simply edit this targeted object, and here I'll put in quotes cylinder, oxygen cylinder. And now in the output you'll be able to see both of the objects have been detected. Now let us see. Let us detect man and woman. In the target I am putting as man, classes as man. I am passing an image where man and woman are present. Let me pass man as well as woman. Now let me run this. The output that has been generated, you will be able to see woman, man, man, woman, etc. So all these are the capabilities of this model. This model is correctly identifying all of the objects that we are passing in the targeted object. So we have taken so many images, as you are able to see on the screen: chair, table, chair, screen. So we have added targeted audience as object as chair. Few more example where we are passing targeted object as table, sofa, it is correctly detecting. Then the pet detection, we are passing an empty image where only dogs and cats are present and it is getting annotated. So correctly it is getting identified. You can try multiple applications of this project because the range is so wide. Basically, this project was done to understand object detection using this Qwen3-VL model that we have seen. It is more like a very emerging topic in AI today, and the main idea behind us developing this project was to see how a model can detect multiple objects from an image or like understand them using language. So this was the core concept behind the project. I hope you all have liked it. If you have any queries, you can reach out to us. We will provide you the documentation also. In case you have any queries, you can also go through that documentation. So that was all for this today. In the upcoming series of the videos, we are going to bring more emerging AI topics. So stay connected, stay tuned with us.